Hello and welcome to today's webinar on increasing polymer sustainability using artificial intelligence. Together with my colleague, Dr. Steve Edkins, Director of Strategy and Operations at Citrine Informatics, I will guide you through today's session. Steve's background lies in materials, and since he started at Citrine back in 2018, he has helped many companies to create value from their data and has a deep understanding on how AI can accelerate product development. My name is Stefan Keller, and I'm a senior account executive, and I'm supporting companies to successfully implement AI in their R&D workflows. I have studied polymer engineering, and before joining Citrine in 2020, I worked for over 2 decades in the polymer industry for companies like GE Plastics, Sabic, and just before Citrine, I was working at Polymer, which is now called Avient. During today's session, we will be covering the following topics. We will start off with introducing you to Citrine Informatics. Working with many customers in the polymer industry, we would like to share with you what we have learned to be seen as key challenges of our industry, mainly facing in the field of product development. We will continue to show you how Citrine can help address those challenges before I will hand over to my colleague Steve, who will demonstrate 3 different cases on how this is practically done. We will conclude the webinar with a Q&A session. Here again, I would like to encourage you to put your question in the chat during the session. We are going to answer them at the end. So let's talk about Citrine Informatics first. Citrine Informatics provides a cloud-based software platform that enables material scientists, researchers, chemists, formulation developers to access cutting-edge AI and machine learning with a minimum learning curve. So you do not need to be a data scientist or a software engineer to use it effectively. Our approach to doing this is by tailoring our AI to be able to learn from small and sparse data sets, which we are typically seeing in the chemicals and materials world, as every lab trial is expensive and time-consuming. We enable experts with a scientific workflow and a graphical user interface to teach these AI models with information which is not only captured in the training data, but also in the brains of the scientists. We call this materials and chemicals aware. The research and development, as well as the application development teams at our customers, are using the Citrine platform in their daily work to solve their materials development problems faster and push the frontiers of the materials they are working on. Citrine Informatics started the AI journey in materials and chemicals over 11 years ago. We are headquartered in the Silicon Valley and have a global team in place supporting our customers wherever they are. To give you a sense about our customer base, it covers a broad range of clients from Fortune 500 companies down to even small startups across a large variety of different material classes, including batteries, glass, semiconductors, metals and alloys, or more broadly spoken, liquid or solid formulations, such as paints and coatings, adhesives, or polymer compounds. Looking at the logos, you might realize that we are also working across the entire value chain, from raw material ingredient providers up to product companies, which are finally manufacturing end products. If we talk about chemical companies, we are working with 4 of the top 10 global companies. The same applies for the adhesives and sealants market. And in the personal care market, we are working with 2 of the top 10 companies. Talking to companies and working with our customers in the polymers world, these are the common challenges which we are hearing. They state things like, we need to be able to overcome supply issues. We need to reformulate our existing portfolio and replace harmful ingredients, such as PFAS. We need to comply with new regulatory requirements, such as the packaging regulations. We need to overcome the price volatility of ingredients. In addition to that, we, as end customers, are more demanding than ever. In the past, we were mainly looking for a good performance of a product at a reasonable price. Now, there is a new dimension. Customers are now, in addition, demanding more sustainable content in a product, but still keeping the performance high. Everybody in that industry sees the need to act more agile and move faster to new, more sustainable solutions. So how does Citrine help with regards to sustainability? Number one is accelerated material ingredient substitution, which boils down to removing harmful ingredients, substituting crude oil-based chemicals with a bio-based content, or using more post-consumer or post-industrial feedstock. Number two is linked to enabling them to reduce the energy needed to process material. Here, the focus is often on developing new processes or modified processes which consume less energy. Think about Scope 2 emissions. Number three is helping customers to come up with products which are, for example, lighter or enable them to use the product longer, addressing the whole value chain, meaning Scope 3 emissions at the end of the day. So let's dive into some real examples. We are working with the largest producer of thermoplastic resins on multiple projects. One was focusing on reducing the amount of fossil-derived oil used and moved to a more bio-based content. When we started that project, they were envisioning a fairly long development time due to the complexity of the project. Applying AI and machine learning enabled them to reduce the time to replace 90% fossil with bio-derived polymers by 50%. Another company we work with has a specialty in cellulosic biopolymers. They could see customer demand for green plastics and wanted to build on their expertise in this area. We helped them screen different possible combinations of new ingredients using their domain knowledge and modeled thermal properties. They have now an AI workflow to rapidly identify and validate new polymers. Using cellulose as a feedstock captures greenhouse gases, and our customers' cellulosic fiber are being used in high-performance clothing nowadays. At a medical device manufacturer, they calculated the potential of reduction in CO2 emissions. The goal for that product was not only to optimize for cost, but also to optimize for CO2 footprint. So they developed an AI model with predicting capabilities to predict the CO2 footprint and optimize the product at the same time. Finally, an example from an automotive application where the goal was to come up with a more lightweight solution to either increase the range for e-vehicles or to improve the mileage for combustion engine cars. Goal was here to come up with a lighter polypropylene grade. This customer was able to decrease time to market and captures over 50 million in additional revenue by using the Citrine platform. So the range of application and applicability to improve sustainability with AI polymers is pretty broad. With that, I would like to hand over to Steve, who is going to demonstrate the applicability of the Citrine platform with 3 different use cases. Over to you, Steve.
Thanks, Stefan. What I'm going to show you now is how to solve 3 sustainability-focused problems using workflows on the Citrine platform. I'll start by showing you how to use our design workflow to reformulate grades to replace environmentally problematic additives such as PFAS. I'll then show you how to use the Model Explorer to make predictions that enable you to incorporate more recycled content into your grades while dealing with the challenges arising from highly variable feedstocks, such as those coming from post-consumer recycled material. I'll then finish by showing you how to use our data manager and knowledge assistant workflows to simultaneously optimize for the mechanical properties and socio-environmental factors of grades, such as greenhouse gas emissions or ecotoxicity. Citrine platform has a simple workflow that starts with dragging and dropping your test data into the platform as an Excel file. Then, using no code at all, you can use that data to train an AI model that predicts the key properties of your materials. You can even build your expert knowledge into those models just by teaching the model like you would a human using natural language. Once you have that model, you can use it to test ideas in silico. So if you have an idea for a formulation that you think is promising or a change to a formulation, you just punch that into the model and it will quickly give you a prediction that helps you sanity check that idea. The search space is where you set constraints on your materials or formulations that make sure that the candidates that the platform is suggesting are feasible both from a technical and from a business perspective. Finally, candidates is where you tell the platform what the targets are for the key properties of your material. It then returns to you candidate materials that are entirely new, that have a high probability of satisfying those targets. So then you look through those and you select some which are safe bets, some which are more exploratory. You take them to the lab to test them, and then you can put those results back into the data set to train that AI model, make your AI model smarter for the next go around. Now we're looking at the Citrine platform, and we see those same 4 elements of the workflow represented here: data, AI model, search base, and candidates. In this example, what I'm trying to do is reformulate an ABS plastic to keep the same spec for the physical properties, but to find a replacement for a banned class of flame retardants. And you see that represented here. So I have my ABS formulations data set. I'm using that to train an AI model that predicts things like the flexural modulus, tensile strength, flame rating. My search space says I need a flame retardant, but I can't use OctaBD or DecaBD. That's these banned flame retardants. And then in candidates, this is where I'm telling the platform what the spec is. So in this case, I need a flexural modulus above 360,000 PSI. So now let's dive into each part of that workflow individually. Let's click into the data set now. This is where we keep data on our formulations and raw materials, which are relevant to the project. To add data, we go to Data Manager, Add New Data, and this is where I drag and drop that Excel file of my formulations and test results. They get uploaded into the platform, and they're ready to use for AI. Going back to the data set now, let's take a look at how the data is represented in the Citrine platform. Data in the Citrine platform is represented in what we call materials histories. That's a complete graphical representation of the process history of that material from raw materials all the way through to testing. So in this case, what we can see is we have raw materials, which are being mixed together in specific amounts. You go into a drying process. That powder then goes through an extrusion process with a lubricant, and the pellets coming out of that extrusion process are then made into a part by an injection molding process. We can click into any of these individual processes to see what the process parameters used were. So in this case, I can see the mold temperature was 30 degrees C. For the injection molding, if I go to the extrusion process, I can see that the screw RPM was 100 RPM and the final zone temperature was 245 degrees C. What this does is it really takes the guesswork out of interpreting historical data that you did not produce yourself. I'm sure many of you have encountered a scenario where perhaps a colleague that has moved on to a different company created some data in the past using their own Excel template, using their own conventions. You find it on a shared drive, but you can't exactly tell what happened there. How did they actually make that material? What were the specific raw materials used? What were the process parameters? It really gets to the point where that data isn't reusable. This solves that problem by taking the guesswork out of it so that anybody can come to a piece of data, a material that was made in the past, and know exactly what raw materials were used and what processes were used to make it. In the data set, we can also look at the raw materials that we have available for this project. So let's do that. We see some resins. Let's scroll down. Let's take a look at OctaBDE, one of those banned flame retardants. I see here I have some properties about that flame retardant, its molecular structure, molecular weight, density. I can put in the cost of that material for us to procure. And I can also look at the molecular formula. The Citrine platform gives me a lot of tools to manage and interpret my data. I can plot the key properties of the material against each other. It also shows me distributions, which point out to me where there are outliers in the data, which may be that a test wasn't performed to the correct specification, or maybe it was just a typo that I need to go in and fix. it also shows me where I have sparsity in my data. That is, where do I have missing values? So for instance, here it's telling me a lot of the properties I have 100% coverage on those measurements, but I only have flame rating for 80% of my formulations. So maybe that's somewhere I need to invest in making additional measurements there, or maybe not. Maybe that's okay. What I want to do now is show you how a chemist or a formulator that might not have any prior experience with AI or machine learning can, in a matter of minutes, build an AI model that predicts the key properties of their formulations and that understands the underlying chemistry of the materials that they're working with. So let's click here, select create new. And the first way that the software enables this is it provides a really intelligent, chemically aware default model. So it looks through those material histories I showed you. It identifies all of the processes, process parameters, the raw materials, any measured properties of those raw materials, molecular structures, inorganic structures. It takes all those pieces of chemical information and it uses them as inputs to the AI model to predict the key properties. So this is the first way. It's a really intelligent, chemically aware default. So you see in this model here, we have our training data, that intelligent default chemical description of the materials is in these boxes here. And those are being used then down in these purple boxes to predict key properties such as specific gravity, flexural modulus, tensile strength, flame rating. So now how does a chemist or formulator use their expert knowledge of the materials to customize this model to make it even more predictive? The first way is that I can click into any part of this AI model and completely customize it just by clicking around with the mouse. But there's an even easier way. Let's go over to our Catalyst Secure Digital Assistant. It's asking me, would I like help editing this AI model? And I would. So what this is going to enable me to do is teach the AI model in my own words what's important about the chemistry and physics for predicting the properties of these materials. So let's say that tensile strength should depend on flex mod. Now what it's doing is interpreting that. It's looking at the AI model. It's figuring out how do I build that piece of information into this model to make it more predictive. So let's apply that change. Let's have a look what it's done. Okay, so I told it that tensile strength should depend on flex mod or flexural modulus. And so what it's done is broken out tensile strength from this ML model so that the prediction for flexural modulus is feeding into the input for the model predicting tensile strength. So it's implementing that change I asked for. Let's try another one. One thing that you might know about this type of compounded plastic is that something that's very predictive of the mechanical properties is the ratio of the filler and fiber to the resin. And so actually that's one of the things it's suggesting I try out here. So let's try that. The fill factor of filler plus fiber over resin is important to my predictions. Okay, it's figured out how it's going to make that change. Let's take a look. Okay, so let's scroll over to here and zoom in a bit. What has it done? It's made a custom formula for me. Okay, so what's happening here? Okay, so this is a custom equation that's being built into the AI model, and it's taken what I said to the digital assistant that filler plus fiber over resin is going to be predictive of the mechanical properties, and then it's found the relevant variables within the model, the fiber share, the ABS resin share, and the filler share, and it's using those pieces of information to implement this equation that I told it. Okay, great. Let's try one more. So back to the digital assistant. Let's say the aromatic bond count in the flame retardant is important for predicting flame rating. Okay, it's found a change it can make there. Okay, let's take a look. Okay, so it's made a change to the molecular structure box here. Let's take a look. What has it done? Okay, it's found the aromatic bond count, and it's included that as one of the molecular structure features that it's pulling out of the flame retardant, and it's going to use as an input to one of the models. So you can see this is really flexible. It's really intuitive. You can teach the model all about your materials, your chemistry in your own words. One of the things that's really important to emphasize about Citrine's AI models is that they're not black boxes. The platform gives you a lot of tools to understand how the models are making their predictions. What do they view as being important for making those predictions? Let's click on tensile strength for an example. If we scroll down here to the feature importances, what these feature importances are telling you, it's a ranked list from most important to least important of which inputs to the model does it think are most important for predicting this property. So tensile strength in this case. And what it's telling us is it thinks the most important properties here are the amount of fiber and also the tensile strength of that fiber. So for those of you familiar with these materials, nothing earth-shattering. It makes sense that the amount of fiber that's going into the plastic and the tensile strength of those fibers would be highly predictive of the tensile strength. But what it is telling you is these models understand that. They are using sensible, physically relevant information to make their predictions, and that increases my trust in the model that it's using the correct information to make these predictions. Now let's take a look at the search space. And as a reminder, the search space is where we place constraints on the formulation and processing space so that we're only focusing the AI model on looking at regions where we have both a feasibility from a technical and a business perspective. So this is where we might put things like constraints on the total cost of the raw materials, which raw materials can we use and in what ratios. So let's click into it and take a look. So here what I'm seeing is some constraints I've placed on classes of raws. So for instance, we've got a constraint that the ABS resin share, so there might be multiple types of ABS resin, but just the resin share must be between 50% and 100%. And then I have similar constraints on the other types of components here, like antioxidant, fiber, filler, flame retardant. So that's constraints on classes of raws. I can also place constraints on individual raws. And this is where we're going to put the really important constraint on the flame retardant. So let's go down to the flame retardants here. So as a reminder, we need to exclude decabromodiphenyl ether and octabromodiphenyl ether. So what we've done here is go to this box here and say exclude for those. And then for the other flame retardants, we said that we can include them. If I wanted to, I could also put constraints on what is the share of those or the fraction of those that goes in the formulation. I can also put constraints on the ratio of ingredients, and I can also put constraints on the process parameters. Okay, so now we're in the home stretch, and it's time to go to candidates. And as a reminder, that's where we tell the software what is the spec for the material we're trying to design. So what I've done is I've told the platform that I need a flexural modulus that's greater than 360,000 PSI. I need a flame rating that's V0 or V1. I need a notched ISOD impact at 73 Fahrenheit that's between 2.5 foot-pounds per inch, 4.5 foot-pounds per inch. And I need a specific gravity between 1.1 and 1.5. Then what the platform is doing is using my AI model, applying that to the search space, and returning to me new candidate materials that I've never tested before. I have a high probability of satisfying those constraints, and importantly, that do not include those banned flame retardants. So it's giving me a list of those candidate materials here, ranked from most to least likely of satisfying those constraints. And I can also see them plotted here over on the right. So I'm plotting impact strength against flexural modulus. And I can see, yes, I've got a decent number of candidates going up towards 360,000 PSI. And yes, they are over 2.5 on the notched impact. So things are looking good. How else can I explore these candidates? Let's go over to the filters. This is where I can apply filters and that apply colors on the plot to different sets of candidates based on some criteria. So this helps me explore and understand what candidates are being suggested. So for instance, these green ones, what we've done is say, please highlight everything that has more than 50% of this specific ABS resin, which is ABS resin 8. Another thing here is, let's just highlight everything that has a flexural modulus that's greater than 355,000. To pull out another example, I can also do something like, I need to have resin 5 used, so ABS resin 5 needs to be in the formulation. And then I can put something like a filter on the processing parameter. So here we're saying you need ABS resin 5 and a drying time between 0 and 2 hours. And you can see that I could use an and or an or here. So this is a really nice way of being able to explore what types of candidates are being suggested by the platform, see if they match up with your intuition. You can also pin candidates, so you can come back to them later. So these are the ones in black, and I can turn that on or off. How do I do that? I press the pin over here. So let's dive deeper into one of these candidates. We've seen the performance plotted, but let's understand more about what the formulation, the processing parameters are. So let's click here into the highest ranked candidate. What I'm looking at now is a visualization of the predictions for the key properties of this formulation. So flexural modulus, ISOD impact, and specific gravity. And one of the key things to note here is that I'm not just getting a single number for the prediction, I'm getting an uncertainty as well. And that's indicated by the error bars here. And what this is telling me is that, okay, so this error bar, the prediction and the error bars are fully within the green area here for ISOD. So we're good on ISOD, same for specific gravity. For flexural modulus, my prediction is 358,131. And if you remember, the target's 360,000. So we're below that on the prediction, but with the error bar, that goes well above 360,000. So what that's telling us, this is probably still a good candidate to take to the lab. It's still likely to have a good chance of hitting the spec, because that uncertainty gives us a strong probability that this will actually be above 360,000 PSI. And I've looked at the outputs, or the properties of the material. Let's go and look at the raw materials, the amounts that are being used, and in the process parameters. So on the left-hand side here, we have a view of that in terms of the component types. So resin, filler, fiber, how much of each of those component types makes up this formulation. And then on the right-hand side, what we have is that broken down into individual raw materials. So a specific ABS resin, so ABS resin 9, a specific filler, kaolin, and the same for additives as well. And then we can go and look at the process parameters. So it's giving us suggested values for all of the key process parameters for both the drying step, the extrusion step, and the molding step. So to recap what we just did, we dragged and dropped an Excel file of our historical formulations and tests to upload them into the platform. We used that data along with our expert knowledge about the chemistry and physics of these materials to build an AI model that predicts the key properties. We defined a search space that excludes these banned halogenated flame retardants. And then we told the software a spec, and it returned to us new, previously untested candidate materials that have a high probability of satisfying all of those constraints. Now I've moved to a workflow we call the Model Explorer. And this is where we're going to start digging into how we use this workflow to start incorporating recycled resins into our formulation and dealing with the high variability that comes with those feedstocks. But before we do that, let's just get a quick understanding of how this workflow works. So what this workflow is really good for is quickly checking an idea you have for a new formulation or a tweak you want to make to a formulation. So in this case, we're looking at one of the formulations that was in our data set, and I'm going to make a small change to it. So let's go down to this filler. We're using cotton, and let's swap it out. Let's look for Kevlar. Let's put Kevlar in. Okay, confirm that. Run prediction. The key things to look out for here are the green cross is the original value, and the purple square is the value predicted after we've made that change. So swapping out the cotton for Kevlar. Okay, so perhaps as we might expect, we've put in a really stiff filler, Kevlar, and the flexural modulus has gone way up. Again, as we might expect, with the flexural modulus going up, because this material is stiffer now with that Kevlar in, the impact strength has come down. Okay, not earth-shattering for anybody that knows anything about these materials, but what this does is really, for me, it builds trust that this model really understands the underlying physics and chemistry of what's going on here, so that when I do go and make a more subtle change, one that perhaps I don't have as good intuition for, I can have more confidence that the prediction is giving me is a really well-informed and grounded prediction. How do I use this workflow to start formulating using recycled resins that I may not have used before? I might not have any data on how I've used them before. And that are highly variable lot to lot. So if you go and characterize those lots of post-consumer recycled resin, there's a high variability in the physical properties that you would measure between those lots. Okay, well, the first thing is, let's look at this existing formulation. We're going to say, instead of using this virgin resin, we need to use a recycled resin. So first of all, let's see what happens if we swap out for a recycled resin. Okay, let's go for recycled resin A. We'll keep the same amount in. We can run a prediction, see what happens. And you can go and see how the properties are changing. Something to highlight here is that recycled resin A has not been used in any of the formulations that were actually measured and used to train the model. Because we build all of that chemistry into the model itself, it's able to predict how totally unseen raw materials are going to behave in a formulation. Now let's see what happens if we move to another lot of that recycled resin. Okay, and then you can see how the predictions are updating. So this enables you to see, what is my lot-to-lot variation going to be in the properties of the formulation in production? And then I can either actually tune things in production to account for the characterized properties of those different lots of recycled material, or I can design the formulation so it's going to be robust to that lot-to-lot variation. Now I'm going to go to Data Manager. Data Manager is where you can see all of the data that's associated with projects to which you have access. Let's imagine that I work in tech service and I get a call from a customer. They tell me that they need a compounded PVC that has tensile strength greater than 10 megapascals and an elongation at break greater than 200%. And it's for a marine application. How might I use Data Manager to quickly see if we have something that's going to fit the bill for them? So first of all, I need to find the PVCs. So let's search for those. Okay, great. I found the PVC formulations. Going to pull all of those up. Now I need to look for something with the right physical properties. So we need a tensile strength greater than 10 megapascals. Okay, great. Filter down to those. And then we wanted to have something with an elongation at break that is greater than 200%. Okay, it looks like I've got a good number. Let's see. Okay, so plotting elongation at break against the tensile strength. Okay, perfect. Well, as I might expect, there's a trade-off between those two properties. The customer also mentioned to me that really the elongation at break is, the most important property for them. So let's go with the one that has the highest elongation at break and see what's going on there. Okay, great. So I've highlighted that. You'll see if we go in the drop down here, we also have some other properties available. So we don't just have the physical properties, but we've also got some life cycle assessment data here that tells us things about global warming potential, ozone formation potential, marine ecotoxicity, carcinogenic for human toxicity. So let's go and see if this is going to be carcinogenic or not. Well, it looks like it's going to be one of the more carcinogenic here if we're looking at the human carcinogenic factor. Why might that be? I think this is one where we want to go and dive into what exactly is the formulation here. Okay, so we click on that. Let's go and look what's going on. Okay, so we have cadmium stearate. Maybe that's what's going on. So this is another case where we can call on our Catalyst digital assistant to help us out. So let's go over there. Is cadmium stearate carcinogenic? So what this is doing now is searching through a knowledge bank that you may have uploaded from your own documents. So you might have technical data sheets, safety data sheets, internal reports. And it's also searching through a curated set of academic literature about chemistry and material science. And it's taking your question and then trying to synthesize an answer using only the knowledge that's in those documents, and then return you an answer and references. So what's it found? Okay, it's found that cadmium stearate is classified as a carcinogen. Okay, well, that seems like that might be the problem for us then. I remember this was for a marine application. So let's see. Is cadmium stearate a marine ecotoxin? Okay, it does seem that cadmium stearate is classified as a marine ecotoxin. It's very toxic to aquatic life. So this isn't really going to work for our customer's application. So this is where we might go back to some of those other formulations we found by filtering, or we might go to the design workflow I showed you earlier to see how can we find a replacement additive for cadmium stearate that is going to give us the same performance, but not be as toxic and be suitable for the marine application. One of the things I really want to emphasize about the Catalyst Knowledge Assistant, which is the workflow I'm looking at here, is it's secure and private. None of the questions you asked are being saved, and nothing is being used to retrain models that are being used by anybody else. It's entirely private to you. The other thing I want to emphasize is that unlike many AI tools, it's designed not to hallucinate or answer when it doesn't know the answer. So it's trained specifically to only answer if the information to give you that answer is contained within the documents that you uploaded or in the academic knowledge bank. So let's see. To illustrate that, let's ask, is this demo over? It doesn't know, so it doesn't tell you the answer. However, I do know the answer. The demo is over. Over to you, Stefan.
Thanks a lot, Steve, for that really clear demonstration of the Citrine platform. As you can see, I would highlight two very closely linked to the topic of today. One is the value of AI in polymers, a white paper which we have published on identifying the value which AI can bring in the polymers world. And the second topic is linked specifically to the area of sustainability, where we were focusing how AI can help companies to reformulate with regards to recycled content. We have far more documentation on our website, so feel free to use the QR code on the right side to get copies of those papers. Thank you for attending today's webinar. I would like to summarize briefly the key takeaways. First is AI helps you to reformulate quicker. The Citrine platform is easy to adapt and easy to be used by each and every scientist. And third, the Citrine team has a decade of experience of rolling out AI in companies like yours. With that, I would like to open the floor for questions. So please feel free to add your question into the chat, and Steve and I are more than happy to answer those in the coming minutes. Thank you.
Stefan, how much training is needed to use this software?
Yeah, regarding the training which is needed to use the software, you have seen the demo and how easy it is usable with a graphical user interface. What we are seeing on our customer base is that once the scientists, even without any data science expertise, get trained through our team, even in the first couple of days, they are in a position already to use the platform, not necessarily directly independent, but over the course of the first couple of weeks, they are in a position to use the platform pretty autonomously from us.
Great. Well, we do have a question in the chat. So it said, for the recycled resins, what data was fed in? So I can take that one. So it really depends on what you have. I think the most impactful way of doing that is if we're looking at trying to understand or predict the impact of the lot-to-lot variability in those recycled resins, it would be whatever information you have on a C of A related to that. So sort of physical properties characterized of that lot, or if you've done any if you do any characterization in-house yourself, you would use that. Okay, let's see. How much initial Excel data would the model need to make meaningful predictions? This is a great question. It's probably one of the most common questions we get. So typically, the size of data set that we are working with when we're working with customers in the chemicals industry is somewhere between 20 to 100 data points. By data points there, I mean sort of unique blends or formulations. So we can work with anything from around 10 upwards. The way to think about this is not necessarily how much data do I need to have a pinpoint accurate model, because that's actually quite a lot. But you don't need a pinpoint accurate model to make progress here for this to be an effective tool, because if you remember, what it's doing is really recommending to you the next formulation that I should try. So the benchmark here is, can I reduce the number of trials I need to do before I hit a target to get that product to market, for instance? And so for that, we can be very effective with between, I would say, 20 and 100 data points. The more the better, but we can supplement the data scarcity or the small data set with your expert knowledge about the materials that we build into the model. Okay, another question here is, what would be the approximate cost? Is it easily available in the market? So in terms of the cost of the Citrine platform, which is our product, there's not a one-size-fits-all answer to that. So we work with companies which are Fortune 50 companies all the way to early stage startups. And they have very diverse needs. And so we have different packages designed to meet different needs there. And even within the same similar size companies, there are sort of different needs depending on whether you already have your own data science teams that might be supporting it, whether you want more support from Citrine, because we always provide our expert support there. And so what I'll say is we have packages to really meet everyone where they are. And so if you're interested, get in touch and we can have a more detailed discussion about what it would look like for your company. Okay, so if there are no more questions, then I think I'll just thank everyone for coming, and don't hesitate to reach out if you want to chat with Stefan or myself. We're more than happy to, and thank you again for coming today.